Hello and welcome to 36th lecture of course on data-enabled tribological engineering from experiments to predictive models. This lecture is the last lecture of this course. That's why we have kept title of this lecture as a future directions in data-enabled tribological engineering. Before starting lecture, let me start with what we have already covered in previous lectures. We earlier covered that data-enabled engineering is transforming understanding, examination, and development of a tribology. And we also mentioned it becomes, or ML becomes, an essential part of tribological landscape. Reason being, the model can learn and adopt. Here, a word I'm using, adopt. That means there is something which is missing in existing theoretical models that can be changed based on experimental learning. So this is very essential for us. So what we can say, ML algorithm can handle excessive or extensive quantities of the data, which we have derived from experiments, from a simulation, from a sensor network. And sensor network, whenever I use a word, it's a real time to decode integrated or is a very complex friction wear and lubrication phenomena. So this ML is very essential for tribology. What we have already covered a CNN, and we say this is very important. Most of the case studies now, they are either on artificial neural network or specialized convolution neural network. They have been designed to extract, analyze, and categorize tribological information using convolutional layers, activation functions, pooling layers, and fully connected layers. We can do a lot of things, and one of the case study which we'll be covering in the present lecture will highlight those importance. In another one, we say utilization of the real-time data. We require collection, processing, and decision making based on those data. So that was a data-driven approach, which we are assuming it's a part of data-enabled engineering also. So this can help us to go ahead with the protective maintenance, predictive analytics, and adaptive control system. Adaptive control system is not necessarily mechatronics related. Here we can go ahead with the adaptive lubrication. We can change the lubrication type and that in a real time. However, we do have a number of challenges also which have been explained in previous two lectures. What we were mentioning about the data integrity. Are we sure whatever we are utilizing data, they are really good? Then we also mentioned about the data privacy. We should not be utilizing some data or stealing some data from other persons, which personal data should not come into this. When we mention also one limitation, computational resources are not very extensive. So we really require data which are more meaningful to us. We may require also interdisciplinary collaboration, even a collaboration with industries and a collaboration with R&D institutions so that we can get overall better results. One more point which was emphasized is the standardization of the data formats. We have a number of research publication, data books and books also. But more or less the data which have been quoted or mentioned in those books or articles, they are not standardized. In the future, we really require a standardization of the data, and we need to stick to the ethical principles. We should not go ahead with the cherry picking, because if we are doing those kind of thing, that future will not be sustainable and we will not be able to interpret the right results. So we really require a good guidelines to think about the future of tribological engineering. If we have got some 10 data, 50 data, 100 data, we should mention all those data. Even though we can give our interpretation, quite possible the future innovators or other students or other researchers, they can interpret in slightly different manner, and we should give the freedom to them. One more thing which we have learned is how to cover a number of numerical methods, or a method which can really help us to predict the friction, wear, and lubrication phenomena. We studied something like a statistical algorithm, and we've also found that they are very good, very effective, but most of the time it is really required a manual feature extraction, and then we also have a little difficulty whenever there is a large scale data. Another one, we will learn something about expert system where the rule based learning comes, and major issue with the rule based learning is the flexibility. They lack flexibility, And then whenever the data are noisy or incomplete, this is very important. Most of the time when we are reviewing the literature or going through the data book, we find the data are incomplete. We don't find all the data in the book itself. So we have incomplete data, and in this situation, this kind of expert system, rule based learning, may not be really very useful. And that's why we say we need to go with ML, and then we learn something like a linear regression, logistic regression, PCA. We also learn that PCA can really reduce the dimension. We also learn something like a sensitivity analysis. We can do sensitivity analysis and we can reduce the number of variables. However, when come to the visualization, which was covered in the previous lecture, we need to go to T-Cine. That's a new method, and then we try to really give better visualization in 2D itself, even though it is a multi-dimension. It can be 5 dimension, 6 dimension, but when you go for visualization, T-Cine will be able to help us. Of course, we mentioned very detailed that ANN and CNN in a number of lectures. We have covered these topics again. We say each mathematical model or numerical model or ML code have some sort of unique strength and as well as a weaknesses. We need to experiment at least 2 3 different methods to ascertain that which is the most suitable one for our application. Again, we say there's no universally applicable algorithm, so we need to think about those. It's not a one research paper suggests some ML model and we start working on that. We need to really figure out what are the strengths, what are the weaknesses, are these really relevant to our work or our problem which is in our hand. Now let me start with one case study, and a case study which has been published in 2023, and I like this title. First is the digital twin. In previous lectures also we given the emphasis that the future is a digital twin. One, this case, intelligent fault diagnosis of the rolling element bearing. Even the word has been kept a fault, and even in the paper they have considered failures, not only the fault. Fault, I assume it's a kind of minuscule or smaller scale, while they have assumed almost failure kind of thing. And then they have focused on the ruling element bearing, which we have covered in several lectures also. Most of the basics of related to rolling element bearing have been covered in our previous lecture. What the most important thing comes is something like a partial domain adoption network, which is very essential whenever we are going for the futuristic approach. What we are doing for time being, like when we were thinking about regression model, most of the time whatever the data we have, and we were comparing with that, and we are trying to match so the ANN model can give the very good accuracy. We never thought partial domain, we say full domain, we were adopting a full domain. But now in this we are mentioning about the partial domain so that we can have a multi resources available to us. There are number of books, number of research article, and every article, every book will give only the partial information. So is our method applicable to those? So what is really relevant for the research or whatever problem in our hand, that only the feature can be adopted. So that's why we say partial domain adoption network. It's a specialized neural network architecture to facilitate adoption from source domain. It can be various source domain, and then maybe comparing with the target domain, like we do experiments where only partial information is available for the adoption. So we are going to take only the partial information, reason being published literature or whatever available to us at our hand, it is not complete. Even there are 3 failures, but we are taking only the partial information, and we are going to train the neural network that there is a possibility fourth failure may come or fifth failure may come up, and that may be a combination of first and second failure or second and third failure also. So that kind of information is very much required for a ML algorithm for that purpose. So what we say, unlike a traditional domain adoption approaches which we were doing in all our previous lectures, that assumes a complete alignment between the source and target domains we were comparing. We are saying there is a target domain, and whatever source data, they should match 100%. That's why we were talking about R square, MSC level, and we say very high 0.99, 0.98. But that doesn't make much sense over here. Reason being, the most of the resources which we'll be having, which will be the partial, and will be providing the partial information. So that way we really require, so we say partial domain adoption method acknowledges. Now here the important thing, presence of domain shift. So when we are conducting experiment across the world in a different lab, there's a possibility there will be some sort of change. Material may be changed, so uncertainty will be there. And what information really is related to us, that only can be adopted. So maybe out of 100 data, but we are not doing purposefully, we are not doing intentionally. We are training our algorithm so that relevant information are being obtained. We are not manipulating. We are not really cherry picking those data, but we are giving information to the neural network that you go ahead with this partial information and maybe partial information from other sources, and then use artificial intelligence to really connect this or connect the missing links, so that overall failure or all of kind of the failure can be simulated properly. Now, if we have a cracks of the 2 mm or maybe say 2 micron, a lot of information is missing in between, are we able to really train our neural network so the all in between, whatever the stages, that can be bridged with this kind of algorithms. So that's why we say aim to adopt model while considering the differences between the domains. So we are not really saying 100% matching has to be done. We pick up the relevant information and we move to next. That's why we say incorporate mechanisms to selectively adopt to relevant information. This is what I have been mentioning, relevant information, while disregarding irrelevant information. So many times we say outliers. We say that this information is because of some noise that can be really removed. That means we say that outlier data points can be removed by algorithm itself. We are not doing purposefully, we are really training algorithm in a manner so that only a partial adoption happens or relevant information being obtained. Irrelevant information, outlier data can be rejected. So if we have a 25 data and we know that 2 or 3 data or outlier can be rejected, and then we again do reprocessing of that. So that's what we really required approach, and that I'm leaving for the future. We have not covered in detail about those topics. However, this case study is trying to give some sort of a knowledge so that it can be covered in the future. Let me cover one failure which we have covered in the lecture 1. We showed that the big roller bearing, the 4 roller bearing, of course in this case we had shown a 2 in this 3D model, 4 roller bearing failed, and that in a very short span of time, like 100 to 150 hours, and each bearing was costing something like a 3.5 million INR. People were not worried only for the bearing failure. They were more worried about the everyday loss. The downtime cost per day was around 10 million. So this is very important. Whenever this kind of a big bearings or very sophisticated bearings or very critical bearings have been engaged, naturally we really required some sort of a active condition monitoring, which again people have been doing it. Now when we go with the partial adoption, we can improve the capabilities, we can improve the processing in a manner so that we get optimum results every time. Earlier it was basically failure or no failure, and then now we are talking, now whatever the process is going wrong, that should be corrected. If the lubrication selection is wrong, that should be corrected. If there is an alignment or because of the assembly time there is a misalignment to some extent, that should be corrected. So we don't want failure, we want to correct at the fault stage itself. We don't want to go to the failure side. So what we say, by harnessing historical performance data and sensor reading, engineers can proactively identify potential issues. There is a misalignment in the beginning itself is being identified. We don't have to wait for the bearing failure, thereby mitigating downtime and optimizing operational efficiency. This is what I mentioned, that we really require to work on operational efficiencies, which earlier cases and condition based monitoring they were not incorporating. It was only the fault diagnosis or failure diagnosis. operational efficiency, like if the friction force is increasing, wastage is increasing, temperature increasing, there was not much information available. Now it is possible to do it, and that's why we say sensor network can act as eyes and ears of the system, and we should act according to that. So we are learning from human being, and then how they act, how they really do operational efficiency, enhance operational efficiency. If we are able to incorporate in our software or ML algorithm, that will be more useful. One more thing which we learn in lecture 4 is something like a pity on a bearing, and it is often mathematically calculated. Okay, fitting life will be something like a 10^9 cycle, 10^10 cycle. Those are all the mathematical models which been done. Sometimes this fitting life becomes much lesser, and sometimes it's much longer. So that's why we say that if we are able to monitor that also, it will really go for the sustainability. We don't have to waste the bearings, because I have seen many times the bearings are opened, and then again assemble. If they check it, that whether the maintenance is fine, or there are generation of bits there or not, so that there is a lot of wastage of time. But if the sensor can provide a complete health of the bearing itself, then we don't have to spend too much money on the maintenance. So what we can say here, the surface fatigue, and here we always use the word surface fatigue and fracture, because what if the pits are getting generated in the process, the material is getting removed from a surface, and whenever the particle is getting removed from a surface, it will be a part of the fracture mechanics. So that's why we say surface fatigue plus fracture. Pitting occurs when high contact stresses will occur, and we know very well in the rolling element bearing, contact stresses can go to more than 2 gigapascal between the rolling contacts, leading to removal of the small particle. That's what we say, that it will be called as a fracture from a surface, causing a fatigue failure. We say pitting is specifically a result of repeated high contact stresses. In addition, now how do we monitor all? How do we know the pitting is going to happen? I can monitor the friction. I can monitor the some variation in sliding speed itself, even though it's a rolling element bearing, but there will be some sort of sliding. And if the sliding increases, that's very clear that something is wrong and the pit is getting generated. Even we can monitor the lubricant quality. If there is a grease, we cannot do that much, but if the liquid lubrication, then we can monitor that. If a temperature is easier one, we can monitor the temperature. We can monitor the, if we are able to capture the images of the ring, then we can monitor the surface roughness also, and all this will be affecting the performance. However, easiest way for most of the researcher is to monitor the vibration, because if the friction is increasing, vibration will change. If sliding is happening, vibration will happen. If there is some sort of degradation of grease, vibration will occur. If increase in the temperature, again vibration will occur. Surface softness change, again vibration will occur. So they assume that vibration phenomena will be better option. However, in my view, vibration is important, but in addition, if you are able to find out the temperature, if you are able to really locate the surface defect or surface softness, temperature and surface roughness effects can give also information. So instead of relying only on one sensor, if you go for a couple of sensors and then take a judgment, it will be always much more fruitful. So what we can say, data driven methodologies to optimize the performance by capturing changes in frictional behavior. As I mentioned, that because of the pitting, or when pitting started, frictional behavior will change. Not only this, if the liquid lubricant performance also will change, or lubricant qualities also can be observed easily. Now if we are able to do this, then we don't have to worry. As I said initially, that the 40,000 hours, this was a life of the bearing, and that was based on a theoretical models or empirical model with the curve fitting methods. So instead of those, directly we monitor the bearing performance, optimize the performance. So instead of 40,000 hours operation, we can go for the 200,000 also hours of operation. Okay, in last lecture we also mentioned, or maybe say lecture 30, we also mentioned we need to do a cost analysis also. If this benefit is coming and we are really spending too much money on a condition monitoring, or capturing data and accessing data, and that information is not really enhancing too much, we are losing a lot, there's a possibility we may not go for conditional monitoring. However, I'm assuming in the future most of the sensor will be cost effective, and then this kind of monitoring will be very helpful. There will be a number of norms from a government also towards the sustainability. From sustainability point of view, this kind of information is very essential and we should do it. So what we say, we should integrate the data streams from different sources, and that so that we can understand the system in better manner, and allow to take a decision in a better action, or maybe say better decision, and then whatever we want to achieve, optimization that can be achieved from this kind of approaches. We learned something in lecture 11 about Hertz in contact, and we mentioned very clearly as a load increases, like a 6% load film thickness and 100% load film thickness, its not variation is significant. That's a very beautiful thing about it. That's the beauty of the elastohydromal lubrication. Now it can be ball bearing, it can be roller bearing. Reason being the film thickness, which is uh, lubricant film thickness, is almost very small. We did some sort of calculation and then compared the results. Now here the also I mentioned when we operate the bearing in EHL domain, even fluid viscosity is playing a very important role. Reason be it gets a thicken, and then the viscosity can increase by 20 times also. So that will carry the load, and then not necessarily material directly has to carry, and there is a possibility of stress distribution that will be very useful. We also covered one example just to demonstrate some sort of numbers. We showed that the P maximum can reach to the 2 gigapascal, and contact width was something like a 299 micron or 300 micron. That's what has been shown. That was covered in lecture 11. Similarly, we covered about elastohydral lubrication and film thickness. We covered one example and we found the results of H minimum or minimum film thickness is something like a 0.055 micron, which is very small, and surface roughness has to be monitored properly. Here we were talking about surface roughness, but misalignment also will come into picture, because misalignment is a major cause of the problem. That's what I have understood. So that's why when we cover this kind of example and incorporate a misalignment, it will give why the bearings are failing. It's not a simple pitting, it's not a simple one fault which is causing a problem. So most of the example which are covered in the literature, they give only few unique failures, but in reality one failure causes other failure, other causes a failure causes a third failure, fourth failure. So there is a combination of failure, and that's what we say in future we require much more sophisticated models to get a real results. So we say even minor failure in a bearing can significantly compromise overall performance of rotating machinery. So bearing failure identification is very important. Of course, I'm not again and again using the word. Instead of thinking about the failure, think about fault. Don't think about the failure. So that's why they filed the diagnosis of the rolling element bearing is crucial to ensure reliability. And here using the word reliability or sustainability, we don't want a component to fail and causes the losses of energy and material. In addition, it will be also safety and economical efficiency also. So bearing fault diagnosis is very important. So we are covering the case study related to that, and what is the additional information the case study is providing. We'll be discussing about those things. However, how do we go ahead with the predictive maintenance and condition monitoring, which we have already learned in our previous lecture? We say generally we start with the data collection. This always first thing is the data collection. It can be vibration data, it can be temperature data, acoustic emission data, even the current consumption, how much current is consumed. So that friction loss can be indirectly calculated based on that. That is also possible. So this information comes from a bearing or equipment where the bearings are installed. We try to utilize the ML algorithm for the feature extraction, and then feature extraction can be several type of feature extraction. We already covered one example where we extract a frequency domain, and then we say related to vibration signal. We also plotted something like a time domain. We did as times as in the synchronized averaging also, some statistical method like R square, R skewness, kurtosis, and many more parameters can be also extracted based on that. Then becomes a model training, whatever the extracted features which we believe after sensitivity analysis, these features are very important. Those features need to be trained, we calculated using some sort of a theoretical model. We are also getting from experiments and we try to compare it so that we are able to establish some sort of differences, and then our model or ANN model is getting really updated using those kind of training. Then is the anomaly detection. We say whatever trend, and then we are able to separate where is a crack and where is a no crack, or bearing is a healthy condition, or some sort of defects have been expected or observed, that should be there. So we say any deviation coming from expected behavior can be named as an anomaly, and then we require continuous monitoring of those sensor data. Often we do automation, we don't want to do manual check. So for that purpose, what we do, we use a threshold setting. What is the meaning of threshold setting? Is something like we covered in earlier one of the lecture. We say that pitting density is more than 5% or more than 20%, then the alarm should be set. Or in this say pitting density is a 1%, or maybe in the first crack has been identified, cross check should be there. That's why I'm using, instead of one sensor, 2 3 sensors should be used, and 2 3 sensors are confirming the same information, then we can go ahead with the alarming system. However, in this case what has been shown, the threshold setting appropriate threshold is a crucial for anomaly detection. Threshold can be determined based on historical data, or we have some sort of experiential learning expert knowledge. So we can say 5%, 10%, or 1% based on, or maybe say crack line more than 50 micron, then only the alarm should come. That can be used that way. So that's why we say anomalous behavior that surpass these threshold trigger the alerts and maintenance. Again, most of the industries, this kind of information is already available. They have been practicing same thing in last, even since last 20 plus years. And then we mention also the validation and optimization. Often we do training of the model, and then we validate, and then we go ahead with the optimization using the sensitivity analysis also. But this question comes, all this have been already done in literature and people have been doing, they are happy with this kind of information. So question comes, so what ML is going to add? In case of ML, we are also looking for innovation side. We are looking something that which is was not earlier easier to interpret. We are also making some models which can be optimized. That is the addition of the ML. Earlier we were doing some sort of design and then manufacturing, then condition monitoring, and condition monitoring was exclusively used to find out the fault or failure and give information. There is a bearing going to be fail in after 100 hours or 50 hours, you be ready for the bearing replacement. So those information are already there and people are using. But in ML we are now able to think about innovation, and then we are able to optimize utilizing the models which have been developed by ANN or CNN, and then we are able to improve the performance. Now this is what we say integration with the maintenance system. Whether maintenance is really required or not, that can be also connected with this kind of data capturing, validation and analysis. So we say the integrate with a maintenance management system to schedule the maintenance activity proactively. When anomalies are detected, work order can automatically be generated and maintenance personnel can be alerted. So this is a information. Again, there should not be false alarm. That's why I'm again emphasizing, if we are getting a similar data with more than 2 sensors, that will be more advisable. Instead of looking only in the vibration data or acceleration data and judging this on that, instead of that, if you go for 2 3 different sensors, and that will be really important to us. Last one in this case is a continuous monitoring and improvement. This is what I'm giving again emphasis, that improvement. Earlier it was whatever has come, we will go ahead with this. Now we are continuously thinking from sustainability point of view, how to reduce the energy consumption, how to minimize the failure. So whatever was happening at the 40,000 hours, can you really extend to the life to the 200,000 hours? That's what we mention here. So bearing anomaly detection is an ongoing process that requires a continuous monitoring and improvement. By implementing effective strategy, industries can reduce downtime, that's what I mentioned, prevent catastrophic failures, extend the lifespan of equipment, and optimize the maintenance schedule also. So this is what we have already covered in our previous lectures. I'm just trying to summarize in this short manner. And this also was covered in lecture 21. We mentioned about the bearing, and we say how do we go ahead with diagnosis of the bearing fault. This has been already covered, and whatever the case study which we are going to cover in the present course, that is related to all these things. So in this case, what we did, there was once the test setup, and then we mount first a healthy bearing, next faulty bearing, and we capture the time signals, and then response of the acceleration being recorded or sensor being recorded. Then we do evaluation of the fast Fourier transformer. We try to analyze and we try to figure out what are the fault frequencies, and then if fault frequency are clearly indicating the failure, then we need to think about making a model which is robust enough. So in this case, first we go ahead with the healthy bearing, then go for the faulty bearing, and then we repeat experiments results 3 times or 4 times and diagnose the results. And already we know what are the defect frequency of the rolling element bearing, because rolling element bearing will have an inner ring, will have a balls or rollers, outer ring sometime we have a cage also. So we know very well the defect frequency. If any of the defect on the inner ring or outer ring or a rolling element, there will be some frequency characteristics or signatures. And if we capture this time signal data, convert to FFT, and then get a frequency domain knowledge or a spectra, that will allow us to understand what kind of a failure we are going to get on the bearings. So this is what already been covered, and this was also covered in earlier lecture. The same, we say that there are a frequency signals. We say the ball pass frequency outer ring, ball pass frequency inner ring, ball spin frequency, fundamental train frequency, the FR, or maybe the cage frequency. There are some mathematical models in the available in the literature, and then we know very well there is a pitch circle diameter, and that's why the pitch circle diameter has been given, the rolling aluminum diameter. So these relations are there. Again, the beta angle is something like what is if it is a 0, that means complete radial load. If it is a some angle, that means there is some sort of a load also coming in axial direction, which is trying to press a rolling element bearing in axial direction. Otherwise, the beta is 0, then it is a complete radial load. So this has been already covered in our lectures, and then converting to the frequency domain data, and that has been shown over here. You can see peak here, peak here, peak here, peak here, and then this is a healthy bearings. Now when we are coming to the faulty bearings, we are also getting the similar kind of peaks. You can see here faults. Now and here also the fault, here is also fault, and here is also fault. Now only the difference comes in this case is what are the additional side bands or additional some frequency data which is coming nearby that also. So by analyzing in detail, that can give more information. However, again, only in frequency based domain may not give 100% correct results. So we need to analyze appropriately. Now here in this case, you particularly can see third harmonic is giving a very high value compared to the third harmonic in healthy bearing. But in coming to the this one, we say 1250, and here is 800. That means in this case, even the bearing is healthy, it gives us some sort of misalignment. So to check it, again we really require some other data. However, this has been already covered, and then that's why the case study which we are going to cover, they did an experiment almost 6 times. So when we unmount bearing and again assemble bearing, there are some possibilities of the change. It can be because of the noise, because of alignment. So that need to be ensured that whatever we have done, it is correct. There's a possibility of noise, there's a possibility of extra elements that should be removed or cleaned properly before really doing a good analysis. So we'll come back to the case study, which as I mentioned published in 2023, and as I mentioned, they are really utilizing a digital twin. And one more thing which I mentioned is a partial domain adoption network. They are assuming that something which is available, we are going to only fraction of that. As I say that the traditional data-driven fault diagnosis method requires obtaining a data set of full failure modes in advance. So this is one of the limitation. Unless we have all kind of database related to the failures, we cannot train it properly. most of time it is not available, so we have only partial information availability. So we say availability of data set is a major issue that gives this kind of algorithm or whatever they have used algorithm some sort of upper hand, because we say then this kind of shortage of the data or maybe lack of the data impairs the practicability of the data driven fault diagnosis method for a various application. And to get a solution, that's why we are saying partial domain adoption network should be utilized. So digital twin, which establishes a virtual representation of physical entity with some sort of operating condition, it can really also generate some sort of fault diagnosis for the rolling element bearing when data are insufficient. In other words, what we are saying, if I am able to make a digital twin model appropriately, so I am able to get some sort of mathematical formulation in that, some sort of relation in that, and I can really do some sort of simulation to generate data which are not available to us. So that is what we say, wherever the partial data are available or incomplete data are available, we can do a digital twin after doing some sort of training to the model and then generate some sort of data which are insufficient. However, again, this is not giving 100% assurance to us, but an attempt can be made that whatever there is a shortage of the data, can we really do simulation? It's something like that. We did experiments on a 1200 rpm, then we did an experiment on 1800 rpm. We know very well in between we can really do some sort of a mathematical modeling, and if the model was giving satisfying result at the 1200 rpm and 1800 rpm, in between we can really get a data from a mathematical model. Similarly, if there are some information which are missing, mathematical model or the digital twin model can be utilized to furnish those information. So that's what has been mentioned over here. So now to cover this case study, we are giving overview. What we say, initially they made a dynamic model based digital twin model, and operating condition of actual rolling bearing that would establish. Then digital twin model facilitated some sort of simulated fault data set. Now inner ring failure, outer ring failure, rolling element failure, those kind of information can be given, and we can really do simulation. So it will be basically mathematical, it will not be experimental. However, we are going to give information what we can really do experiment subsequently, so that we can do validation. So it compasses various operating condition and fault failure modes of the rolling element bearing. Again, this is again single failure, one failure at a time, that may give us different thing. Now if two failure happen simultaneously, if we are not feeding those data also in our experiments or maybe say mathematical model, it will be incomplete. So if I go ahead with the four different failure modes, and then if there is some sort of interaction between those failure modes, and if we are not able to simulate, then there will be problem. However, if the digital model is giving a good result at the four failure of the modes or different failures, then that also can be corrected. So in what we say, based on this we can do some sort of a transformer based cross domain deep neural network learning, and then we can provide some sort of information to the system. Now here the two things are coming. We are saying whatever the simulated data which we have already understood, we are using the word labeled data, and then whatever we are measuring or we are doing performing experiment, those are unlabeled data, because when whatever we are getting experimental measurement, those are data are not labeled. But when we do theoretical, we already know what are the assumption, those are the labeled data, and then we try to compare this data and do a transformer based across deep neural network that will be able to provide us some sort of better learning. Now what they did, they analyzed the two cylindrical bearings. So you can see here is N 205 and U205. Of course, EMA is basically enhanced load carrying capacity. 205 is kind of bearing series. 05 means a 25 bore. However, there, as I mentioned, that in one case it is only N, another case is NU that has been shown, and is a basically without flange on outer ring, and NU is a with a flange on outer ring. Why we use the flange as outer ring? So that it can sustain somewhat axial load also. And if you look at now, in this case diameter is also on a higher side, all other parameters are same, number of rolls are same, angle beta is a 0, this diameter has been shown on a higher side. Otherwise pitch circle diameter same, bore diameter same, and OD is also same. That has been shown, and that is what they have done in this case. Now this is a very interesting which is they have done. They use a selective adversarial strategy to introduce a cross domain feature alignment. This is a new thing which we have not learned in this course, and that's why I'm using the word it should be done in the future. Reason being, we are doing this because we don't have data from experimental analysis. So wherever data are missing and we have not done it, that can be utilized. They can be generated using a selective adversarial strategy. That's what model they have utilized for this purpose. And we say digital twin driven fault diagnosis framework can be made based on this, where the labeled data and unlabeled data, which is measured data, can be incorporated. So overall algorithm will use both. We try to minimize the differences, and then there is a possibility we generate a new additional data wherever the measured data are missing, so that overall information can be utilized in an effective manner. Again, if there are some data which are missing, that also can be generated using the digital twin model. So this is the way the digital twin model can be improved. Again, I'm saying this may not be complete. Maybe they have done for the 3 or 4 different faults, but when a real fault comes, it can be a combination of that. So it is a continuous learning, and we are assuming over the period this kind of digital model will be giving far better results compared to what we are getting now. Of course, it is giving far better results compared to what we used to get from condition monitoring or directly analyzing the data. And then that was already pre-decided there's a crack or there's no crack. So those things were already embedded in system. And then we were doing this kind of analysis. So here we are talking about the futuristic, we are failure which we are not seen. That also can be predicted using the digital twin model. So this is a complete framework which have been provided by this paper. So what are these framework? You can see here, and we say establishment of the dynamic model based digital twin model for the reflecting operating condition of actual rolling element bearings. So we are not performing experiments in utilizing digital this model. We are able to simulate what are the damping coefficient, what are the stiffness coefficient on the every location of the rolling element bearing. Then they are generating some sort of faults. It can be fault at the inner ring, outer ring, and rolling element bearing. So they are looking at the 3 different faults. They are able to simulate their signals also. So if there is a fault at the outer ring, what kind of signals can be generated? If there is some sort of fault on the rolling element bearing, what kind of the faults can be generated or maybe simulated? And then if it is inner ring, what kind of the signature will be getting, or what kind of responses will be getting? So here this is what we are saying, everything else is being simulated. Now once we do simulation, it need to be compared with experimental data. That is also there. Now this is what we say unlabeled measured vibration signals. This is a label because we already have generated from our assumption that there is a fault at the outer ring, there is a fault at the inner ring, there are fault at the rolling element bearing. So we already have labeled, we know we have information with the way. While in this case we don't have that information earlier, we are detecting. Of course, when they are engaging the bearing, they are generating failures their own. That time they will be knowing. That means there is already labeled data. But in future, faults may not be known to us. We need to go with this digital model. We are training first on the bearing by creating faults. After that, this complete digital twin model can be exposed to the unknown bearing which has not been passed through the failures. Maybe the new bearing, and then we are connecting with the digital twin model with that, and we have not generated any failure or any fault on the outer ring or rolling element bearing. While initially for the training purpose we are generating those faults, getting signals, we are comparing it, but future it may not be. So whenever we get a signal, we can estimate, yeah, there is some fault on the outer ring, there is some fault in the inner ring. Again, is it really different? No, it's the same what condition monitoring was already being doing. But here a combination of those faults can be simulated, response can be simulated, and then we can check it. Or if we are getting some response from experiment back, we can analyze those signals, and then we can say, yeah, there are some sort of fault which was not initially thought over. Now we are getting those faults in a bearing, and it should be treated in the future. So this is from a future point of view, it is good. Now this t-SNE model also been shown so that visualization happens properly, and then we are able to see, yeah, there are three different faults. Yeah, blue color is totally separate, orange color is totally separate, pink color is totally separated, so that we are able to distinguish the failures. It is a really much lesser overlap. If model is not very good, then there will be a lot of overlap. Now this is what we are showing here, and then this is a generation of the simulated fault data set, enabling simulation of various operating condition and fault failure modes. Once we have a digital twin model which is being complete in every sense with a known kind of failures, we can think over, we can create our own faults and see the response also in that. In this case, we see these experiments were conducted to demonstrate the efficiency of whatever the model has been created and the usefulness of the model in practical industrial bearing fault diagnosis. So whatever they have developed, so this is a one slide, they have shown complete thing. There are bearings, then there are mathematical models of then the computer models based on that, then the signal generation on from this, and signal generation being compared with experimental signal which will be measured and related to the different kind of the bearing faults. And then if we are trying to establish that whatever they have done simulation, it is ensuring efficiency and complete reliance on that. Now what kind of faults they have generated, this is what we again picking from the same literature, the paper has reference has been given. One is a normal one, the fresh bearing, no fault at all. Then bearing fault, you can see outer ring there is a fault over here, and then response will be according to that. Then there is a rolling element fault, and finally there is a inner ring fault. So there are fault they have shown, and based on that they estimated what kind of a acceleration data will be there. So this is a complete mathematical model. They are able to simulate, they are able to give a vibration signal or accelerometer signals that has been shown. And this is what we already also covered in our one of the lecture slide, that ball pass frequency at the outer ring, ball pass frequency at the inner ring, ball spin frequency, the relation has been given here. You can see maximum frequency will be when there is a failure at the inner ring, and minimum frequency value will be when there is a failure at the outer ring, and in between the because of the ball frequency or with the failure of the ball. So this three has been shown in here. And now this slide shows a comparison. Waveform is a t and the time series, envelope is the frequency series, and you are able to see ball fault, inner ring fault and outer ring fault. And this is a three waveform, they have been shown figure 9. This is basically a fault at the inner race, and this is a fault at the ball, and this fault is a outer race. So there figure 7 shows over here that way. Now this is what they are getting response. You can see here when they did a simulation, the first frequency comes something like a 108.1 hertz, and then they got it from experiment, it is a 107.5, so very close accuracy. Now coming to the this ball fault, they found the frequency at the 115 hertz, and this is a 113 hertz. While coming to the inner ring, they found at the 155.3, and here also 155.3. So this has been shown. The theoretical fault frequency for outer ring is a 108, ball frequency is a 115, and inner frequency is a 155. All the same. Now but you look at in this case, as I mentioned earlier, when we do a theoretical simulation we get a clean signals, but when we measure we get a some sort of a disturbances. You can see the disturbance here, disturbance here, disturbance here. So experimentally whenever we measure we get a lot of noise in that. Now similarly in this case, on the ball one also you can see that there are some of a sideband they are getting, and here they are much more thicker. So it is not the 100% we are able to match, but wherever it is important, whatever the characteristic feature of inner ring failure, outer ring failure or ball failure, they are able to compare the results, not all. Now if we are getting this additional signals over here, is it because of the noise or something else? If there is something else, that should be diagnosis. So that when we go with a complete digital twin model, we should be able to simulate each and everything. It's not only the characteristic frequencies or features which already we know. because this feature also can give us some information or some hidden information, which is our main aim when we go for the detailed analysis. So what we are saying here, the presentation of time domain waveform envelop, there's a frequency domain comparison between simulated and measured signal under fault of outer ring, ball and inner ring, and operating frequency they mention something like a 20 hertz or maybe 1200 rpm. So they have done this analysis, they compare, and then they say that whatever they have simulated they are able to get results, so mathematical model is correct. And then they have suggested overall network architecture. You can see the source data or source domain, that is simulated one, this is experimental one. They are using a feature extractor, and one of the previous studies we have mentioned that feature extractor CNN can be used a feature extractor, and this is a complete final neural network and the layer can be given. Subsequently they are going for the classifier and domain discriminator. Now this is important for us. So you can see the feature extraction, that as I mentioned, they extract the feature capturing the discrepancies between simulated and measured data. Coming to the classifier, it gives a what kind of fault. So output prediction for the both simulated and measured data. So here we are not giving CNN or feature extractor, whether we are giving some information related to simulation or the measured one. We are giving information, and based on that the classifier is deciding what is the real thing. But major point comes, which is a different in this paper, is a domain discriminator. Domain discriminator, that's what has been shown with the D, is implementation for adversarial learning in a shared feature space to achieve the domain invariant representation. What is the meaning of domain invariant representation? As I say, from one literature to other literature things vary, and we want to minimize those, and we want to minimize by going with a partial adoption, not a complete adoption. Earlier whatever we were doing, it was a complete adoption. Now here we are thinking about a partial adoption. So that's why we say in this overall network the three main components: feature extractor, classifier and domain discriminator. That's what I'm mentioning. It's a new here we have not discussed earlier. Earlier we were talking about something like classifier, regression and feature extractor. So in this case, what is the first step? Is the initial step feeding simulated source sample and measure target sample simultaneously into the feature extractor to extract the different features related to various health conditions. So this is was done, and then these all are the cost functions which need to be minimized so that the discrepancies are as low as possible. So this is overall network which they have mentioned. Now as I mentioned here, that main distinction between the what we already covered and this covered in this case study is a domain discriminator model. What is that? It's a this model is aimed to reduce feature distribution discrepancies between the simulated domain and real world domain, meaning to minimize it. But we are saying utilization of adversarial learning strategy, and that learning strategy is coming from a neural network, that's a domain adversarial neural network, to achieve a domain invariant. That's what I was mentioned in a slide earlier, that we want to capture from a different sources, so that from when you're shifting from one domain to other domain there should not be significant change in that. And that's why they have shown complete mathematical model and optimization of that. This model has been optimized. The DI is been shown as a something like a domain one, and then this is a feature space, and this is a what we use, they use a word cross entropy loss, which has been given. The cross entropy loss has been given here, and this is a y is a what we say the representative label, which was mostly the domain space. We give a representation or we give a label to that, what kind of failure because of that. And this is on the y this end we will say predictive label, and case is basically what are the health condition, how many health condition we are really checking. Those kind of things have been mentioned. And finally here what we are, they are using gradient reversal layer also. This is a new, we say introduce a shear feature layer to facilitate adversarial learning for achieving domain invariant learning in this case. So these are the somewhat new things which we need to be learned in the future. We are not yet covered those kind of things, but the one good point that we don't have to rely 100%. We need to go with a partial adoption, and then wherever there is an outlier or somewhat difference, either we reject and modify the response from that. So that's what they have been done it. So that's why we can say what are the future direction. We say digital driven cross domain fault diagnosis task. Simulation model provide a monitoring for various health condition, and this will help us to provide a somewhat data which are available in rolling element bearings. Now one point comes, there are already data which are available in literature. Now, if you look at this Western Reserve University Bearing Data Center, most of the research publications have been published based on those data. They utilize those data and make a digital twin model. So here we want to emphasize that's not a correct way. Digital twin model also requires experimental results, and if we are only utilizing one data bank, one data source, then quite possible we are missing something. So that's why I say, however, in real time industrial scenario, specific fault occurring is often unknown in a monitoring data collected, and that's why we require to implement in complete way, because most of the times data are given but not in complete form. So it be adopted as a partially, or we assume those data which are available, they are only partially available, and we update our model the way we showed in previous slide. We update our model by optimizing, by minimizing the discrepancies, and that is where in future we really require more domain knowledge for that purpose. As I mentioned, this is a belonging to the discriminator network. What is the meaning of the discriminator network? We say it provides a difference between real and generated data, and that's a future providing feedback to the generator network. So this is a where the network whatever, even ANN model or theoretical model, it gives it get information to improve the model. We have been emphasizing to improve the accuracy of model. Now here we are going to go ahead with improving the model itself. To generate a realistic sample, basically one or more layers of the neural network, and then it says that it can be a convolutional layer or fully connected layer also. So this is a kind of some suggestion for the future, and then if we are able to implement this in the future, it will provide a good overall results. That's why we say adversarial learning for achieving domain invariant learning involves a training a model to produce features that are indistinguishable between the different domains, whatever the number of domains we are capturing or utilizing, and then we are able to extract the features which are similar, and we are utilizing only those. Wherever there is a difference, we are rejecting completely. That is also one possible, and then we are also updating our model based on that. Again, whatever we do, it again and again need to be refined. So this kind of model will never get saturated. This requires a continuous improvement and effective transfer of the knowledge across the domains. Use a discriminator network, that's what I'm again giving you emphasis, that's in future, that tries to distinguish between the feature from a different domain, simultaneously training a feature extractor network to generate a domain invariant representation. What is the ultimate aim? Ultimate goal is to learn features that are robust to the domain shift from one lab to other lab. Even something is changing, and then we are able to extract the right feature. That's what we are looking forward in the future, ensuring that model performance remain consistent across a different data set or different environment. If the humidity is changing, temperature is changing, we are getting similar results, or whatever the model we have utilized, that has a capabilities to distinguish, or maybe say those models also, or maybe that environment also, or different data set also. So those are very important to really come up with the results. They also publish some results, I'm just trying to give an analysis on that. So what they did experiment, and then they compare results. You can see the domain adoption is mostly partial, they are not utilizing, and they use a different method. In this case, a total 6 methods have been utilized. So what did they say? Utilize a simulated data as a source domain, which we already done. Measure data as a target domain. They took a two cases. One is a 1200 rpm as a running case. Other one is 1800 rpm. And then in each case, they use the 4 health conditions. What are the health condition? As I say, one, there's no crack, nothing, no fault. one fault on inner ring, one fault on outer ring, and one rolling element bearing. So there are 4 cases. Again, they have not considered simultaneously cases. So there are some limitations. Naturally, every publication will have some limitations. However, to avoid the noise, what they did, they conducted experiments 6 times. Even the theoretical, when we are using deep neural network, we know we go with a random number and we need to generate again and again. And if experiments are done a number of times, then we get a more reliability. So they did this kind of experiment, whether by utilizing the deep neural network or experiments. If you do a 6 times, then it really provides a much more confidence on those results. Now they compared results and then has been shown doesn't make much sense to us as such, but comparison, as I say, in this case, no domain adoption was utilized, other partial domain adoptions, and then this is what they mentioned, and they have utilized a scheme to get a better results. And everywhere they have shown whatever that they suggested, that is giving a better results compared to better accuracy compared to the other proposed model, whether case A, whether case B, and that's why they say that whatever they are suggested, that is giving good results and should be relied. Ticini also visualization, you can see here, that's what is shown. When they are using no domain adoption method, they find a lot of overlap. While they are using any other thing, there is a some overlap, better over and compared to other. However, in their model, they are able to get a much more segregation, much more accuracy compared to other. So this has been mentioned. It's a feature obtained by domain adoption or mixed, and it gives misclassification. And all other cases also, they are finding some sort of overlap. Proposed method exhibit discriminative feature distribution with a clearer decision boundary, and this has been shown here. Of course, there is some overlap, of course, and as I mentioned, they have okay, use of 4 health conditions. The only thing which you are able to see here, that we find only 3. We don't have a 4th color, and that's why whether they have not found any failure in the outer ring. No failure at the outer ring has been observed, so they have plotted only 3. That's a failure on the inner ring and a failure at the outer ring, and no failure. That's what has been shown over here, and that's what has been shown. IF inner ring failure, ball failure, and is a no failure in this case. They also utilize a confusion matrix, which is also somewhat different for me in this case, because they could not get any failure of the outer ring. That's why they have used NaN. That's not applicable for this. And then almost in all the cases, and then again they showed in their model is giving good results except the ball pass frequency, where the accuracy is coming something like a 0.6. And then CNN here accuracy is 0.62, while accuracy in case of IF in this case is 0.8, and their proposal is a 0.89, here is 0.94, and this proposal is a 0.96. So what do they say? The source domain simulated data has a 4 health condition, while target domain measured data have only 3 condition, because there was no sense no response of OF or the failure at the outer ring. NaN has been used in confusion matrix to indicate no occurrence of OF. And then few example, of course they found some sort of a misclassification in previous diagram also, previous slide also we showed that there is some sort of overlap. Now those overlap is both in a CNN as well as the proposed whatever they have used a method. But here you can see here the ball frequency, they obtain only the 0.6% or with the 60%. So that can be improved in the future. So we can summarize what they have done. They use a digital twin partial domain adoption neural network. This is very important. As I'm again and again I'm mentioning that we should remove the all outlier, that's possible. And then they utilize a selective adversarial strategy to achieve partial domain adoption between the simulated data and measured data. This can reduce the feature distribution discrepancies, and again avoid a negative transfer. If we go with the complete adoption, there is a possibility that we may model something which is not there. We are giving a wrong information to our model. So that need to be clean, or that can be thought in a better manner. And finally they use experiments to establish their effectiveness and superiority of the whatever that they suggested as a model in this case. And what we are seeing, these all other future digital driven approach, fault diagnosis of rolling element bearing is a future. Reason being, we mostly will get insufficient data, and even in presence of insufficient data, how to improve the reliability and safety of the mechanical system. So that's why we really require this kind of methods. And whatever the digital model, it should be also high fidelity model, so that it can really give a right results. It should not give a wrong results. Now, like, coming to the limitations, a major limitation of this study, and then we really need to look at in the future, is saying that they have considered only three kind of the failures: uh, outer race failure, inner race, and ball, and again not simultaneously both. And then they also utilize only for two rotational speed. Doesn't mean that when we operate at 6000 rpm we'll get a similar kind of response, which may have a possibility of to adopt as a generalized equation. Of course, they also never said that they want to go ahead with a generalized one. Another one, as I said, that we need to think about the fault level, not a failure level. We don't want a complete failure. And unfortunate in vibration signal is that if the crack size is smaller than some size, and then it will not be able to give a vibration signal. So that is one of the major limitation of vibration signals. And because there is a major limitation of vibration signal, that's why this limitation of this study also comes from that point of view. And then another thing is that they have not really tried a different kind of fault size. They use a fault at the outer ring, inner ring, and balls. But what are the different kind of the faults on the ball itself, inner ring or outer ring, in presence of one pit, in presence of two pit, in presence of three pit, that they have not done. So that is for the future. And a study does not address the issue of identifying unknown fault modes. As I say, that there is a combination. Now in this case, like this complete failure of the bearing happened because of the misalignment, and then they have not modeled that kind of misalignment, which I believe is very important. Another thing, in these days we are talking about the debris, because if there is some sort of pitting happening, some failure happening, such chip will be released. And if we are able to diagnose, we are able to take a picture of chip or the debris, that will provide a far better predictability. Again, when we go for the chip, you can see a combination of the debris also. It's not a single debris. So this kind of analysis is very much required in the future. Better and better, and minor level, nano level, give always a much more reliability compared to giving complete thing. Yeah, there's a one fault of the outer ring that may not give a completeness. So coming to the future scope, we say we really require more data. We in this case particularly was shown some sort of a simulated data by generating digital twin model, but it may not give a complete complexity. Whatever the model has been trained, it will be giving only those kind of thing. Now we can generate a signal using a combination of mathematical model, and there are some sort of a data driven regression model, like we have shown a number of data which have been already published and is available in the open resources. We can use a combination of this to come up with a better results. We can go ahead with a more realistic data from a fields, actual field, maybe in automobile or industrial, where the bearings have been operated. It's not what we have done and only in the lab level. Actual data will be giving more important information. And then not only whatever method in this case they have suggested, going for the partial domain adoption, but we can go ahead with some other schemes also. There are some sort of a scheme like a self ensembling, self training, curriculum learning. There are a number of other schemes available which can be utilized for this purpose, whatever they have done. Of course, they have done excellent work, and it is really giving a future direction to us. And then we need to talk about something like identifying unknown fault modes in a target domain. Those things are also important to think over what are the subset of the faults which can occur in a source domain as well as the target domain, and we should be able to address those faults. That's why they require a much more work, maybe much advanced course is required for that purpose. With this, I say thank you for your attention. Thank you.